Hello, everyone. Welcome to the RCIF Applied AI Seminar Series, focusing on causal ML for healthcare applications. Today, I'm going to be talking about how causal chains in healthcare modeling can help identify effective treatments utilizing patient data, which can distinguish successful interventions from coincidental recoveries. We can forecast patient responses to treatments, enabling personalized healthcare plans based on predicted outcomes. We can enhance clinical decision-making by providing evidence-based insights, supporting clinicians in making informed decisions about patient care, and we can understand disease progression. This can help unravel the complex causal pathways of disease, facilitating early intervention and preventative strategies. Causality is also extremely important for policy and resource allocation. So it informs healthcare policy and resource allocation by identifying causal factors that significantly impact public health outcomes. In particular, so Lingam stands for linear non-Gaussian acyclic model. So it applies non-Gaussian assumptions. Basically, it identifies causal relationships from data that's assumed to be non-Gaussian, distinguishing it from other causal discovery methods. Basically, it utilizes a directed acyclic graph to represent causal structures with nodes as variables and edges indicating direct causal influences. So we can see an example of a directed acyclic graph on the right where we see different nodes and different edges indicated by arrows. So causal discovery employs statistical techniques such as independent component analysis to uncover the causal order of variables without needing prior knowledge. It can be used in healthcare to analyze patient data to reveal causal factors affecting outcomes, aiding in treatment and policy decisions. Some of the advantages and limitations are that it offers a unique approach to causal inference, particularly when traditional models falter, though its effectiveness depends on the data's adherence to the non-Gaussian and no latent cofounder assumption. So DoY is a Python package created to facilitate causal inference by providing a unified interface for modeling, estimating, and interpreting causal effects. It helps users to identify and validate causal assumptions in their analysis. It utilizes a four-step process, which involves creating a model, identifying, estimating, and refuting. This structured approach ensures rigorous causal analysis by explicitly modeling assumptions and systemically verifying results when you build a model with the DoY structure. There's multiple estimation methods which can be used, which support causal effect estimation. So this includes propensity score matching, instrument variables, and regression discontinuity designs, allowing flexibility and robustness in analysis. It's important to refute and validate the claims made by the models, so it provides tools to refute causal estimates through robustness checks, such as placebo tests and sensitivity analysis, ensuring the credibility of the results. There's different approaches to each. So, for example, Lingam assumes non-Gaussianity to identify causal structure. DoY requires that you come in with some type of hypothesis. In addition, both of these models utilize graphical models to represent the assumption. So you can construct complex graphs from this data. You can use those graphs to make estimations and understand data. It's important to validate both of these models through robustness checks and sensitivity analysis or through statistical tests for causal ordering. They're both fairly flexible. Lingam is specific to linear non-Gaussian models. Both of them can be used for causal inference and can be applied to healthcare or any type of tabular data. In terms of evaluating causal models, it's important to determine that the graph is complete. We need to do a smell test and ensure that the causal graph includes all relevant variables and relationships to accurately represent the data within the data set. It's also important to look at the directionality of the arrows to verify that correctly represent the causal directions between variables based on domain knowledge or prior studies. In terms of conditional independencies, it's important to check that the graph encodes the correct conditional independencies aligning with the data and theoretical expectations. The plausibility of the assumptions needs to be verified as well. Does this make sense? a sensitivity analysis is another good test to validate the model. Let's take a look at Lingam. This is an example code which basically goes through loading a data set within pandas. In this case, I'm utilizing the Duke MRI data set, and we're going to be using that to predict the days to last local recurrence-free assessment from the date of diagnosis for breast cancer patients. So we're setting that as the endpoint. We're showing the different descriptors that are available, and we're utilizing those by splitting the data into X and Y variables and then splitting that with an 80-20 split. We can then use that data to optimize a random forest regression model, where we find the most optimal hyperparameters for the model utilizing a randomized grid search. So we're utilizing randomized search CV here with 5-fold cross-validation. We're then taking that model, which has been optimized, and we're utilizing the most important descriptors to build our causal model. So we've found the feature importances, we're sorting them, and then we're utilizing those top 10 features to build a causal model. So here we're just defining how to build a graph, and we're utilizing the Lingam model to build this causal graph, and we can see the representation of the data and the relationships between the data. So in this case, we are showing that adjuvant anti-HER and EU therapy has an effect on the days to last distance reoccurrence free assessment. There's a negative causal factor, which shows that having this therapy does improve the outcome by reducing the number of days to reoccurrence. We also show that days to surgery also reduces the days to reoccurrence. All of these things kind of pass an initial smell test. This is just a really powerful method for taking data and generating graphs which can be used to understand relationships within complex data. With that, I'm happy to take any questions from the audience and glad to discuss further what we're doing at the CHPC to help facilitate people running codes like this to make discoveries. Thank you and have a good day.